Hi, I'm George Kondiles, Chief Architect and a co-founder here at Ocient. Today, I'll be discussing a little bit about Ocient's zero-copy reliability and data availability scheme. Now, as a distributed system, Ocient, like all others, must be prepared to handle a variety of possible fault and failure scenarios. Anything from a drive failure or a node outage, either transient or permanent, to something like a network split or network access problem. Generally, most systems, when accounting for this, will rely on a replication scheme. Essentially, taking information representing rows to be queried and placing that information on multiple locations, either separate nodes, drives, so on and so forth. Now, this scheme works and enables access to the information in the face of failures. However, it comes at a cost. The cost specifically being the extra storage overhead associated with these extra copies. In a system that is configurable to handle a given degree of fault tolerance, which most systems are, we say that we can support, in this case, up to 2 total losses, 2 faults, at a cost of 3x, 3 times the total required storage. Now, in many cases, this is a perfectly viable solution, but Ocient, as a hyperscale data warehouse, is in the situation where the total amount of information stored is so large that the total cost associated with this multiple here can be cost prohibitive. To account for this, Ocient has taken a different approach to provide for data reliability and availability, specifically one that does not rely on copying. Ocient has deployed an erasure coding scheme at its most fundamental levels, enabled and embedded in not only the storage layer, but the query and data access layer as well, integrated directly into our consensus protocols. The system as a whole understands ownership in an erasure-coded way. Our fundamental storage unit is something that we call a segment. And these are relatively large, on the order of hundreds of megabytes to gigabytes, pieces of information storing in columnar format records for an individual table. At load time, we take multiple segments, let's say for example 2 in this case, and we'll perform erasure coding arithmetic at what we call the coding block boundary level. In this, almost all cases, 4 kilobytes across. The result of doing this is the production of additional segments holding the erasure-coded information, where, because it is an erasure coding scheme, we are able to rebuild a missing data portion from the combination of the remaining data portions and the erasure-coded data. Now, as I mentioned, this is a configurable scheme. I've drawn only a 2 of 3 configuration here to make it easy to place onto the whiteboard. Generally speaking, though, we will deploy a wider scheme, something like a 10 of 12 scheme, allowing for up to and including 2 faults spread over 10 disjoint data units. Now, the primary value of this, when we talk about storage cost and overhead and so on and so forth, is that we can calculate the overhead of the scheme by this simple equation. The number of data units, 2 in our case here, plus the number of faults tolerated, 1 here, over the total data units again. Now, we talked about supporting up to 2 fault tolerances with 3x replication. We can also talk about supporting 1 fault tolerance with 2x replication, where the overhead cost of that would have been obviously 2x. We could do the math for this simple case here as 3 over 2 equals 1.5, and it's easy to see that the total cost here is substantially less, even for this basic scheme. The wider you go, the more cost efficient you can be for the same level of durability and availability, i.e. fault tolerance, as you can with replication. Now, the astute observer might note that segment data here is currently present in only 2 of the 3 segments. And when Ocient lays segments out, we strive to ensure that each individual segment is stored on a separate node. And this gives us node-level fault tolerance, in addition to drive-level fault tolerance. One of the tenets of Ocient's compute-adjacent architecture is that we endeavor to involve as much of the computational and I/O capacity of the system in queries as we possibly can. And if we were in the scenario where a given segment stored only erasure coding data, N2 in this case, a particular query that was accessing data for S0 and S1 would not involve node 2 because it doesn't have any actual table information in it, just the erasure coded data. To account for this, we employ an erasure coding rotation scheme similar to RAID 5 or 6, where at the coding block level, we rotate where the erasure coding data is present in the set of segments, such that while on total we've spread the information out and the ratios are all the same with respect to how much data is real data and how much information is erasure coding data, it's evenly distributed over all of the nodes. So they evenly bear the burden of the storage and all can be involved in queries. Additionally, by virtue of the fact that we access at 4 kilobyte layers, or our block boundaries, we encounter a bit of a problem in that the erasure coding data now is splitting up the data as it's stored on disk. And what this has as an issue is it prohibits us from doing larger scale reads and improving I/O efficiency. To account for this, we employ a mechanism that we call parity squashdown, where we take the erasure coded data and using a bijective function, map it to a different section of the file, enabling us to slide the data blocks up and enable contiguous reads. One final very important element of Ocient's erasure coding data reliability and availability scheme is that it incurs no overhead on the read side in the case of a non-faulted system. This is because individual records are stored intact in their individual data units. We don't split them out over other segments, meaning that when every node is available, all information is available for the drive, so on and so forth, that there is no erasure coding mathematics required to get the information out of the system. The cost on that read is 0 with respect to the erasure coding data. The only time we must perform the erasure coding rebuilding is in the case of a fault, in which case, obviously, there is some overhead, but generally, it is masked by the fact that most of the data is online and available at all times. This has been a bit of an overview of Ocient's zero-copy availability and reliability data scheme. If you have any additional questions or would like more information, please visit our website.